So we can use this to construct our hypothesis test. And that's what we'll work on next, trying to build up this logic. So we can compare the observed difference, the obtained difference, in other words, our sample mean, to what we would expect based on chance. So if we're talking about a treatment, we can say this is the treatment effect we got, the increase or decrease in scores. What would I expect by chance? And is it smaller or greater? Whenever you come across any kind of statistical test in inferential stats, so the Z-test we'll do today is one example, but anything else, a t-test or a correlation, anything else, is always essentially going to be this equation here. It's your obtained difference, the thing you actually saw in your data, the thing you saw change, maybe it's the mean or whatever it might be, divided by the difference that you just expect by chance. In other words, it's the effect you saw divided by your level of uncertainty. And sometimes we refer to that as a signal over noise approach. And so whenever we go and give you equations that show you some kind of test, that's all it's doing. The thing, the observed difference, the observed effect, divided by your level of uncertainty. We can do that here if we're talking about our treatment example, where we've gone out, we've given treatment to some group, we've got their mean, and we want to see, is that mean typical of the population that they came from? When we do the Z-test, what we do is we take the obtained difference, the difference between the mean that we had and the expected population mean. So in our example before, it was 103 compared to 100. And we divide that by the standard error of the mean. So our level of uncertainty, what we'd expect just by chance. And that's essentially what the Z-test is that we'll go through later on. The difference that we would actually saw divided by our level of uncertainty. Now we then get, when we solve that equation, so we put in our mean, our expected population mean, divided by the standard error, we get a value. And then we have to determine, well, how big is that value? And we need a cutoff for that. So the bigger that value is when we solve that equation, the more likely it is that there actually was some kind of treatment effect. The more likely there is that there's a difference between the mean we had and the population mean. But we can't just look at that value and make a judgment. What we do is we decide what a critical value would be for that. How big does that ratio actually have to be before I actually reject my null hypothesis or accept my hypothesis, and we'll talk about what that means. And that's when we have this idea of a significant difference, if it's bigger than our threshold. And we'll talk about how we actually derive that threshold. So this is all building up to our null hypothesis significance testing, or hypothesis testing. We define that as a statistical procedure that uses data from a sample to test the hypothesis about the population. That's what we want to do. And so in very simple terms, if we're interested, if we say, see a difference, and we think it's interesting, what we want to know is, does that difference actually play out in the population? So if I give people treatment and I see an improvement on some score, would that same thing happen if I did it in the population with other people? Or does it just apply to my sample? In other words, is it just random error? It's fundamental to everything we do in statistics, and it allows us to generalize our findings. So if we're not doing this, then all we can ever say is things about our sample, and we're not interested in doing that most of the time. We want to say things about the world at large. So the logic, we have kind of 3 steps. The first thing we do is we select our sample from the population. We're then going to give some kind of treatment to that sample. After the treatment, we then measure the people on whatever score it is that we're interested in. So there are 3 steps. So you might not do this in real life. This is quite a cross-sectional way of doing it. In real life, with a drug trial, you might have a longitudinal study. You might measure them before and measure them afterwards. That's okay. We're just kind of simplifying things. So we take our sample from the population, we give them a treatment, and then we measure afterwards. If the individuals in the sample are noticeably different, we've sort of spoken about how we might define that, from individuals in the original population, we have evidence that the treatment had an effect. But it's possible that we might just get a difference that we observe just because of sampling error. So it depends what random sample. If I've got a mean of 100, perhaps it isn't that the treatment worked at all. Perhaps I just happened to get a really dodgy sample with an IQ of 130. It could happen. It's unlikely, but it could happen. And that's sampling error. So here's a bit of a diagram of what sampling error looks like. It depends generally on a couple of things. If you have a look at the slim distributions here, what they're kind of illustrating is you take a random sample from the top one, another random sample from the same one again, and then another one. And you sort of plot their means, which is the little x's down below. And you can see that you get a bit of variability there. So you're never, as I said before, you're never going to get exactly the same mean as the population, and you're never going to get the same mean twice. It's always going to be a little bit different. And hopefully you're going to get them kind of clustering around the mean. And that's where the most common scores will be. And so that's for a nice slim distribution. If you have a look at a fatter distribution, that the population that has more variability in it, you do the same thing. You take 3 random samples. You notice that you get different sample means. So the sample means are further away from the population. So the more variable a population is, the bigger the difference will be between your sample means and the population mean. So that's one of the things you just need to take into account when you're thinking about it. But the take-home message is that you're going to have variance and differences in your sample means that you take. So just to make that a bit more concrete, let's imagine we have 1,000 students. We know that the average age in that population is 21.3, and the average IQ is 112.5. We take one random sample. We end up with an average age that's a bit lower, 19.8, and an average IQ that's a little bit lower as well. So that could happen. We take another random sample. This time we get an average age that's higher, but still a bit lower than the population. And the IQ that's actually mean IQ that's higher than the population. So just by taking random samples from a population, you're going to have some kind of variability. That's the variation we expect by chance. And that's what we want to quantify and take into account. That's going to be our uncertainty. So when we do our hypothesis test, taking all of that into account, we want to look at 2 possible explanations for the mean that we saw. Thinking about our treatment example, where we've taken a sample, given them a treatment, measured their mean, and we want to know, is their mean different from the population? The first explanation is that the difference between our sample and the population can just be explained by sampling error. That is, it's just natural variation that we get because we took a random sample, and it's never going to be exactly equal to the mean. That would indicate that we don't have a treatment effect. If we're saying it's a sampling error, then we're saying there's no evidence for a strong treatment effect here. So that's the first explanation. The second explanation is that that difference between the sample and the population is far too large to be explained by sampling error alone. And if we have that, and we'll define what we mean by far too large, if we have that, then we can say that there is evidence for a treatment effect, because that mean we got was too different from the population mean to just occur by chance at some level of probability. So when we do our hypothesis test, keep in mind they're the 2 explanations we're trying to decide between. So go back to our cartoon again. We have our known population before our treatment. We have a mean of 80 and a standard deviation of 20. We then take our sample, give them the treatment, and we want to know what is the mean of that population afterwards. Is it going to be a new population because the treatment worked, or is it just the same population? So we take our sample of 25, we go and do it, and this is what we get. So let's go back one. So we have 25 people taken randomly from our population. We have a mean of 92, so we've seen this before. And now we've calculated that we have a standard error of 4. So for that mean of 92, we can go through and calculate a z-score for it. We can ask, where does that mean of 92 fit into the distribution of sample means? It's got a z-score of +3. So we can say it's quite far away from the mean, from the population mean. It's not right on it. It's not a z-score of near 0. It's a z-score of 3. And if you remember back to our cutoff scores, we used, for z-scores, we could talk about 1.96 as being a big cutoff score. We'll talk about those a bit more. But that's a large z-score. So we're saying that mean is very far away from the population mean. And so we can now decide between whether or not the treatment effect had an effect, that is, our treated population mean was equal to the population mean before, or whether, there was no effect, or whether there was an effect and the treatment mean was different somehow. Using that z-score, because we can now fit our sample in to the population.